Okay, at the end of number 8, we saw the piano, and that there was 294 newtons. This 294 here. And this is opposing motion, this magnitude of 294. So in this case, if Jimmy's pushing the piano, obviously he's pushing it here, and he's pushing it with this force in this direction of 100 newtons, the piano's not going to move. He's going to have to push it with a force of more than 294. So that's all this diagram is showing. And the piano, it's takes the lazy way out according to the book, and it just opposes friction with the 100. It doesn't need to oppose it with 294. The same here for Kate. Kate's pushing with a force of 200 newtons. The piano still doesn't budge, but if the two of them push together with this 300 newtons, because there's only 294 opposing, the piano is going to start to move. Might not move very fast, but it is going to move. So what this force is, this 300 newtons is greater than the 294, and this is called the maximum amount of friction, which can be called into play, which is called limiting friction. So very short video here, just take this note on limiting friction. What is it? And then the laws of friction. The first law, the direction of friction is opposite to the direction which the body tends to move. And we saw this, friction will go this way, so we're going to see this in all of our questions. Friction will go this way, the body is going to move this way. The magnitude of friction is up to a certain point equal to the magnitude of the force tending to produce motion. Otherwise, a certain amount of friction will be called into play, and the maximum amount is limiting friction. Just think of the piano example. The ratio of limiting friction to the normal reaction is this mu, and this constant mu is called the coefficient of friction, and depends on the nature of the two surfaces in contact, but not on their size and shape, nor the area of the surface. When motion takes place, the limiting friction still opposes the motion and is independent of the velocity. And in truth, the amount of friction called into play when an object is moving is slightly less than when it's just on the point of moving, but we ignore this slight difference, okay, for mathematical purposes. So let's look at this example here. A sleigh and its occupants, total mass of 500, coefficient of friction is mu, between the sleigh and the snowy ground is 1/10. If a husky dog can pull with a horizontal force of 100, find the limiting friction. Okay, let's just always draw these diagrams the same way. Here's my sleigh, here's my friction, here's my reaction. mg in this case, 500g. And I have the Huskies pulling the sleigh in this direction, and we'll call T the tension on the string or the rope. So we're told that mu is equal to 1/10. This is what we're given. So we can say that or opposing forces, R is equal to 500g. F is equal to mu times R, which is equal to 1/10 by 500g. So F is going to be 50g. And 50 by 9.8 is the same as 98 by 5, which is 490 newtons. So that's my limiting friction. So I need a force greater than 490 to get the sleigh going. And we're told here a husky dog can pull with a force of 100. So this goes into part 2, the least number of dogs. 5 by 100 will give us 500 newtons, which will get the sleigh moving. So we need 5 dogs. Although huskies normally run in pairs, so I would say 6. And the acceleration, if in fact 6 dogs are used, okay, 6 dogs are used in part 3, thank God they have a pair. The acceleration we're looking for now. So if I have 6 dogs, we want 6 dogs, so I have 600 driving it, and I have 490 opposing. So my resultant force is going to be 110, 600 minus 490 is equal to 110 newtons. So F, that's my F is equal to ma, that's my acceleration. So 110 is equal to the mass, which is 500 times the A. So A is equal to 11 over 50, or 110 over 500. So A double 11 is 0.22 ms to the minus 2. So on to the next Video number 9, and we look at some when maybe we're looking at inclined planes in number 9.